So far, you've seen how the A, K, and J scopes work. But remember, we said there was still need for another type of scope. For instance, here's a newly established beachhead on a Pacific island. Because of its advanced position, enemy bombers can attack the island from any point on the compass. Radar coverage is being handled by this SCR 545. Here it is, searching through a full 360 degrees. And there's a target. See it there on the search scope at the right. To find the target's range, you have to stop the antenna and bring it back onto the target. Then crank the pip into the notch on the range scope. To get the azimuth, the pip must be split and balanced on the azimuth scope. Only after you've made these adjustments can you report the range and azimuth of the target. But while you're doing all this with every target you pick up, what about planes in other sectors? As long as the set is looking in one direction, it's blind to everything else around it. So you can see that there was need for a new type of scope, a more versatile one. A scope that would measure both range and azimuth at the same time. One that would enable you to view the whole area at once and thus follow several targets simultaneously. Out of this need came the PPI, Plan Position Indicator. With this scope, no matter how many planes there are in the sky around you, or from what direction they approach, your beam is continually searching and will pick up each one of them. The PPI paints a map for you of the surrounding area. Each target appears as a glowing blob of light at a point on your scope corresponding to its position in the sky. Each time the antenna beam passes over the target, the baseline, which is synchronized with the antenna, repaints the target blips on your scope. Thus, you can watch the movement of any number of targets at the same time without trouble or delay. Here's a sample of a PPI scope. And to show you how accurate a picture it presents of the surrounding area, here's the actual map. In developing this PPI scope, a new type of cathode ray tube had to be worked out. In order to project both range and azimuth at the same time, the deflecting plates inside the tube were replaced by a pair of coils around the neck of the tube on the outside. This is the other type of tube we mentioned earlier, the electromagnetic cathode ray tube. Let's look at the tube and coils from the front. When current is sent through the coils, it sets up a magnetic field between them. That deflects the electron beam away from center. As more current flows through the coils, the magnetic field between them gets stronger, and the farther off center the beam is deflected. As the current decreases, the electron beam returns to its normal center position. The deflection of the beam from center is always proportional to the amount of current flowing through the coils. And of course, just as on the A-scope, the deflection of the beam is synchronized with each transmitted pulse. When you apply current in the form of sawtooth voltage, you get the familiar trace and snapback movement of the electron beam. When it is speeded up, there's your PPI baseline, composed, as it was on the A-scope, of an electron beam sweeping back and forth so rapidly it creates the illusion of a solid line. When a target signal reaches the indicator circuits, it causes a greater number of electrons to be fired through the tube. The increased flow lasts for only an instant. Then the stream returns to normal, but the result on the scope is an intense glow of light at that point on the baseline, which represents the range of the target. Since each time the antenna is pointing at the target, there are several thousand pulses sent out and several thousand echoes return, the increase in electron flow at that point happens so fast that it forms a steady glow of light on the baseline at the range of the target. Range is measured out from the center of the scope, just as though a range scale were placed beneath the baseline. That blob of light in the center is the same as the main bang on an A-scope. The second blip is the target signal, and range is the distance between them. By the way, the process that makes the signals appear as blobs of light instead of pips is called intensity modulation. Okay, you know how the target signal is formed and how to measure range on this PPI. But how about azimuth? Well, those coils that cause the electron beam to sweep back and forth to form the baseline are designed to rotate freely around the neck of the tube. Since it was the current flowing through the coils that produced the baseline, when the coils rotate, the baseline sweeps around the scope. The rotation of the coils, and hence the sweep of the baseline, is synchronized with the antenna, so that the baseline is always pointing in the same direction as the antenna. So, by calibrating the edge of the scope, you can read the azimuth of the target at a glance. For instance, if a target shows up here, it's no trick at all to report its azimuth as 40 degrees. Notice, too, that since the glow of the target signal persists for some time after the baseline has painted it, you can make very accurate reports. For ease in operation, some sets have range markers as an integral part of the scope presentation, like this PPI on the AN-NPG-1. Some sets, like this AN-CPS-1, a microwave early warning radar, employ both range and azimuth markers on the PPI presentation, like this. If you want to examine a particular sector closer, it's possible to expand the picture by moving the sweep off-center in any direction. Now, one quadrant is blown up to fill the whole scope. This presentation is called the EPI, or Expanded Position Indicator. On other sets, like this searchlight radar, the AN-TPL-1, a pattern of geographical grids is placed over the PPI scope, so you can locate the target in terms of grid coordinates. Another method of PPI operation employs two sets of deflecting coils which do not rotate as the antenna turns. Instead, the flow of current through the coils is regulated so that the resulting electromagnetic force causes the baseline to rotate. For instance, if current flows through these two coils with this polarity, the electron beam or baseline is deflected to one side, so. But if the polarity on the coils is reversed, the baseline is deflected to the other side, like this. Same thing is true of the other set of coils. Current flowing through them one way will deflect the baseline upwards. And a change in polarity will deflect the beam downwards. By synchronizing the flow of current through these coils with the antenna, the baseline will always point in the same direction as the antenna. Thus, by altering the flow of current through the four coils, like this, we can rotate the baseline without rotating the coils, which means we can forget about movable parts, bearings, and the added weight that goes with them. The lightness of this type of PPI makes it very useful for airborne sets. Echoes picked up on an airborne set enable the PPI to project a bird's eye view of the ground. The scope will indicate shorelines, rivers, railroads, ships in a harbor, buoys, even the projecting periscopes of a submerged sub. So the PPI is unusually valuable on bombing missions. In fact, all of the overcast and night bombing raids on both Germany and Japan were made possible by radar. But what about the night fighters that protect the bombers, or that go out to clear the sky of enemy bombers or night raiders? A night fighter pilot is after enemy planes rather than ground targets, and since long-range radar is pretty bulky, a radar-equipped night fighter usually operates with an early warning ground set. This MEW usually operates as a GCI set, ground control interception, and often uses this AN-CPS-4, known as Beavertail or Big Abner, to supply accurate height data. When a new target is picked up, challenged, and doesn't identify itself as friendly, the ground station vectors the night fighter to it. The controller watches the blip of the night fighter, guides him toward the target signal by radio. When the controller sees that the night fighter is close enough to the enemy plane so that its own shorter range, highly accurate radar can take over, he tips off the pilot. Now, having been guided to the approximate position of the bomber, The radar operator in the night fighter can pick him up and trail him with his AI, aircraft interception set. There's the target now. Let's see how these airborne radars work. Here's a diagram of our night fighter on the tail of an enemy bomber. The antenna revolves in a complete circle, but since the night fighter pilot is primarily interested in what's in front of him, only that area is presented on the scope. The rest is blanked out. This area, scanned by the beam, and of course any targets within that area, appear on the indicator or scope screen of the night fighter. A bomber that's ahead and to the right of the night fighter will appear up and to the right on the scope. Since this B-scope is intensity modulated, like the PPI you saw a while ago, the target appears as a glowing blob of light. However, the scope presentation isn't fan-shaped like the sector the beam scans, or like it would appear on the circular PPI. If it were, the short-range echoes would crowd together and be hard to spot. So, for ease of operation, electrical circuits actually stretch the picture into a rectangle. This is the presentation furnished by the airborne B-scope. When you turn on your AI set, this is what you'll see on the B-scope. It measures range vertically from bottom to top and azimuth horizontally. Now that we've seen the presentation, let's see how the B-scope produces this picture. Remember, with an electromagnetic tube, it's current flowing through the set of coils on the side that bend the electron beam up and down. When sawtooth voltage is sent through these side coils, we get the familiar up and snap back movement, thus forming our baseline. The baseline is synchronized with the transmitted pulse, like this. When the transmitter is triggered, the electron beam starts up toward the top of the scope as the pulse goes out. When the beam reaches the top of the tube, the set's maximum range, it snaps back and starts up again with the next transmitted pulse. Since the B-scope has a persistent screen like the PPI, the repeated spillovers form a constant glow at zero range, giving you the familiar main bang. Because the pulse is transmitted hundreds of times every second, the moving electron beam whips up and down so fast that it forms the baseline. Now, when a target is caught in this beam, the returning echo from it will form a blob of light somewhere along the baseline. Zero range is at the bottom of the scope. So if the target moves faster than your night fighter, the range between the two planes increases and the target blip will climb up the baseline toward the top of the scope, maximum range. So that you can spot the range of a target more easily, we can divide the fan-shaped sector which our antenna will sweep with imaginary range markers. For example, every mile, 1 to 5. Then we'll calibrate the face of the tube in the same way, with the 5 grid lines on the scope representing the mile distances in the sky. Here, the target is almost 5 miles away, so its echo appears just below the 5th range marker on the scope. So much for range. For azimuth, we'll add a vertical grid with the 0 marker in the center. Then planes to the left will appear to the left of center on the scope. Those to the right will appear to the right. This target is dead ahead, so it appears on the scope at 0 azimuth. But don't forget, the beam isn't stationary as we've been showing it here. It keeps sweeping through that sector, much faster than this, of course. And since the baseline is synced up with the antenna, each time the beam passes over the target, the baseline repaints the echo on the scope. Here's another target to the left at about 3.5 miles, and there's its echo on the scope. There's another to the right, this time at almost 2 miles. Because of the persistency of the tube, the glow from each target on the screen will be visible until the baseline repaints it on the next sweep. Now let's see how the tube does all this. You've already seen how current flowing through the 2 side coils produced the baseline. Varying the current flowing through the top and bottom coils makes the baseline sweep across the face of the scope. The flow of current through these 2 coils is electrically synced with the antenna, so that the baseline always indicates the direction the antenna is pointing. Of course, since the antenna revolves at 360 RPM, The baseline on the actual scope sweeps across so fast that you can't see it, but it enables you to see the target blip that much better because it repaints the blip so much oftener. As you can see, the B-scope is excellent for helping you find the target and determining his range and azimuth. But in order to line up your guns on him, you must know his elevation. To get that, turn on your range marker and run it up to intersect the target blip. That gates in the C-scope, there at the left. It furnishes you both elevation and azimuth. Here's how it works. To feed data to the C-scope, the antenna, as it revolves, also nods, that is, elevates and depresses slightly. If the beam could trace its movement in the sky, the effect would look like this, painting a series of paths with each stroke a little lower than the preceding one. This is, in effect, what the stream of electrons does on the face of the scope. When the area has been covered from top to bottom, the antenna slowly elevates and the beam repaints the area from bottom to top. By moving up and down this way between the elevation limits of the set, the beam effectively scans all the space within this pyramid-shaped area in front of the night fighter. Any target flying into this area will show up in the C-scope. Let's say our target is right here. When the beam points in this particular direction, it hits the target and echoes are reflected back. Although the antenna revolves at high speed, it moves up and down comparatively slowly, and since there are thousands of transmitted pulses per second, a good many echoes will be returned while the beam is on the target. These returning echoes will brighten a spot on the scope screen at a point that corresponds exactly to the target's position in front of the night fighter. The face of the scope is marked off with a vertical azimuth line and a horizontal elevation line. The point where they intersect is dead ahead of you. Any blips that appear above the horizontal line are from targets higher than you are. Those blips that appear below are from targets lower than you are. So the C-scope is able to give you a scaled-down picture of what you would be able to see with your own eyes if conditions permitted. For example, this enemy plane, which is to the left and below your night fighter, will show up on your C-scope as a blip to the left and below the intersection of your reference lines. To get on target in elevation, you simply maneuver your plane so the blip will come to the intersection. In this case, by turning left and diving slightly, you'll line up on your target. The addition of this clock-type mask enables the radar operator to guide the pilot in clock terms. When the blip is on the crosshairs, you know that you're on target in elevation and azimuth. Keep your eye on the B-scope, and when the blip gets within gun range, open up on him. In these three pictures, you've seen how radar works in principle and have seen many of its wartime applications. The same principles apply, of course, to radar reconverted into peacetime uses. Harbor control, navigation through fog and darkness by ships on the sea and in the air, blind aircraft landings, weather forecasting, meteorology in which radar locates and traces approaching storms, and a whole new field, astronomy, opened up when we made radar contact with the moon. On this sketch of the scope picture, you can see the main bang, and 238,000 miles along the baseline, the echo bounced back from the moon. Here's the actual scope receiving the moon echo. With a souped-up transmitter and hypersensitive receiver, the Echo from the moon appeared as a good-sized pip, 238,000 miles away.